A company wants to know if attending a course on how to be a successful salesperson can increase the average sales of their employees. They sent 6 of the salespeople to attend the course, and we have 1 week sales for those employees before and after they attended the course. We want to determine if the course increases sales at a 5% level and what conditions or assumptions are necessary for the test to be valid. This is an example where we have 2 sets of data that are not independent. They are paired up because what we have is the sales for an employee before and after they went to the course. So we would not expect those 2 numbers to be independent. Someone who is a better salesperson might have 2 high numbers versus someone who is a not good salesperson who might have 2 low numbers. When we have paired data, we start by getting our difference data, and that's just done by subtracting the observations in a pair for the 2 different groups. So you can do this in either order. You can do after minus before or before minus after. That just might impact what you choose for your alternative hypothesis when doing the test. I'm going to do after minus before and get the differences for each of those, and we call those our D. So for the first person, after minus before, 18 minus 12 gives us a 6. 24 minus 18 is 6. 24 minus 25 is negative 1. 14 minus 9 is 5. 19 minus 14 is 5. And 20 minus 16 is 4. So what we're really going to use in this problem are those differences that we just found. We call those our D's, and if you would go through and you would add all of those up, what you'll find is that they sum up to a total of 25. If you sum up those differences squared, what you'll get is number 134. So from that we can find our mean of the differences, D bar, by taking 25 over our sample size, which we treat as 6 because we have 6 salespeople. So even though we started with 12 numbers, we break it down into 6 numbers because we take the differences, and we get a mean of 4.167. Our standard deviation, which we'll just subscript with a D, will be the square root of 134 minus 25 squared divided by our 6 all over 6 minus 1, which is 5. And what we get is a standard deviation of 2.639. So we now have everything we need to get our test statistic. Let's write what we're going to test for. When we're doing these problems where we have a paired example, we're going to test for the mean of the difference data. And we always test if that's equal to 0, which would mean that there is no difference. Here, before and after would produce an average of 0. And now the alternative hypothesis can be influenced by how you chose to do the subtraction. We did after minus before, and in this case, if this course really did increase sales, we would expect after to be bigger than before, and that would mean after minus before would be positive. So we want to test if our mean is greater than 0. Our test statistic will be our D bar minus what we're testing for, which is just 0, over our S of 2.639 divided by the square root of n, which here is 6. And so we get a test statistic here of 3.8678. And this is just like a one sample problem. So our degrees of freedom is n minus 1, and so we have 5. So we're going to go look in our t-table for 3.8678 in row 5. And what we find is that our value is between 3.365 and 4.032, so that our tail area is going to be between 0.01 and 0.005. And we're doing a greater than here, so we don't need to multiply by 2. So this will give us our bounds on our p-value. With a p-value between 0.005 and 0.01, this is less than an alpha of 0.05. And so we will reject the null. So we have significant evidence that the course increases sales on average. And in these problems, if you have a small sample size, which we do since we have a sample of size 6, what you need to know is that your difference data would be normally distributed. So the assumption that we need to make here is that these differences come from a normal distribution.